Hey friends, it's Ben again. This is another video for the differential equations class. This time we're tackling the technique that's referred to as the variation of parameters. I will forewarn you that the variation of parameters um, is time consuming. And you've seen the stuff that I'll go ahead and just work out for you. So you know when I say time consuming, I really do mean time consuming. So keep that in mind. And keep in mind also, you have to be super careful and check all of your arithmetic and your algebra, because if you drop terms, it can just go right square to hell. So, sorry. All right, so the notion of variation parameters. Uh, as you'll recall, we know what to do if we have a homogeneous differential equation, at least the linear homogeneous differential equations. We have something that we can do. We can't always get all of them, all right? But a lot of the ones that we actually need to study, we can solve. So the next thing, of course, was getting what to do if it was a non-homogeneous uh, linear differential equation. And what we found out was if the non-homogeneous term over there, that f of t or g of t or whatever they called it on the right-hand side of the equation, if that was something that we knew was the solution to a linear homogeneous differential equation, then we could kind of make some guesses. Remember that the method of undetermined coefficients essentially reduced to guessing what the answer looked like and then sort of playing with it until we got the right coefficients. That that was the main trick. So that gets you if those things are nice and you can see what kind of differential equation they came from. What if you can't? What if it's something, like a secant or a tangent or something like that that you don't get coming out of these differential equations so far? Then you have to turn to variation of parameters technique. Okay. So let me show you what I've got on my iPad here. All right. So the notion with the variation of parameters technique is that when you start out, and here maybe I will try to make my markings in kind of a big yellow pen. All right. So when you start out, you're able to figure out what the solution to the homogeneous equation is. And the problem that you have is trying to figure out the y sub p. If you can get one y sub p that works, then you've solved the whole thing, because the superposition principle says you just add the general solution of y sub h to that y sub p. So here is our guess this time. Remember with reduction of order, remember how when we looked at that, we said, I know one solution, so I'm going to go ahead and just multiply it by a function that I don't know the value of, and then just plug it back into the equation and hope for the best. That's not, it wasn't that easy, but that's kind of a motivation on it. So here we know the solution to the homogeneous equation. And what we're essentially saying is, those constants that were appearing there, what if they weren't constants? What if they were functions instead? I wonder what would happen. That feels like it's going to get us in trouble. Well, if we're going to plug it back in, then we're going to have to figure out what the y sub p prime and the y sub p double prime are. So when we take y sub p prime, we have to go ahead and use the product rule. And so you get these four terms. Now, here's the tricky bit. We're going to assume that when you take these two pieces here and add them together, somehow they get zero. Is that justified? Well, it turns out in the end it works. So yes-ish, but you would not jump to that conclusion if you were just doing this on your own. This sort of thing here is what persuaded me that I like theoretical math instead of applied math, because there's lots of techniques that just work and you wouldn't guess them, but somebody did guess them at some point. So if we assume that part is equal to 1, then it vanishes. And we get just this. All right. I'm going to take those swashes off there. And yeah. All right. So if that's the case, then our y sub p prime didn't look too bad. And when we try to figure out y sub p double prime, well, it gets messy. But instead of assuming that it's going to be equal to the 0, we're going to assume that it's equal to the g of t that appeared in our non-homogeneous differential equation. Okay. And so if you assume that it caused that portion of it, then what you have actually assumed here in trying to solve this is that your y1 u1 prime plus y2 u2 prime equals 0, and your y1 prime u1 prime plus y2 prime u2 prime equals g of t. Now, the reason that's important is that u1 prime and u2 prime appeared twice there. If you know how to write systems of equations into matrix form, then it turns into this here. And that's important because the matrix I just pointed at is the matrix you took the determinant of to get the Wronskian. If the Wronskian is non-zero, then that matrix we refer to as being invertible, and that means that we can solve the system no matter what G of t is, okay? So to get there, we're gonna make use of something called Cramer's rule. Cramer's rule, I'm just gonna say it in the two-dimensional case and allude to what you do in the three-dimensional case, or higher dimensions. So if you have a system like this, A, B, C, D, E, and F can be anything at all. But if you had a system like that, then the stuff that's over there on the left-hand side, we will refer to as being W, or rather the determinant of it, we'll call W. And then we're going to form W1 by taking the determinant that was W and replacing the first column. W1 has the first column replaced, okay? Replacing the first column with the EF, the column that you had over there on the right-hand side. And W2, you replace the second column, okay? That's the big trick here, is that you are replacing a column. If you needed to do this for a 50 by 50 system, you would go through and replace column 1, column 2, column 3, up to column 50. Don't do that. That's too big of a system to do by hand. That would be crazy. So what Cramer's rule tells you is if you do this, then X, that first variable that appeared up there, will be W1 over W. And the Y, the second one to appear up there, will be W2 over W. Okay? So if you had a Z, W3 over W. So it scales up. All right, so when we're working with this, we're going to take that W and just get the Wronskian, okay? And then our W1, we would take the main diagonal and get 0, minus the transverse diagonal, and that's why we have minus y2 g of t. y2, remember, is not unknown. y2 is a function we already have. And then w2, you'd take the main diagonal, and then you'd subtract the transverse diagonal, which is 0. Okay, so then we can say what u1 prime is, which feels like a bait and switch because now you still have to integrate before you get your answer. But it's going to be something where all the pieces of the function are pretty, I started to say easy to integrate. I'm not going to lie to you. They're going to be something that it takes a little effort to integrate. But once you get that U1 and that U2 from integrating, then you're still not done because you have to plug back in here and multiply them by the Y1 and the Y2 that you started with. Once you get all that, though, you have the actual formula for Y sub P. Now, here is just a word in passing. My students in an algebra class or a Calc 1 class always just want a formula for an answer. And they're always frustrated because I never give it to them. Because to me, doing math is a process, not a formula. If I gave you the formula here, you would decide to go into a field of study that does not involve differential equations because it would just be a horrifying formula. So we've got to remember the process that you go through for that. Take a look in the textbook, make yourself some notes. The only way to get these is to do a bunch of them, okay? You've got for a homework assignment to do like 8 of them. I would advise do more than 8. Look at some of the odd ones in your text in order to get some practice, okay? All right, then let's take a look at a couple of examples here. And in my iPad, I have to hit it in just the right way to get it to do what I want. All right, so this is our first example for the variation parameters. And maybe I overdid it a little bit here, but we're not going to do very many examples, just like 2. So on this, let's make this a little bit less thick. Here on the left-hand side, you can recognize that is linear with constant coefficients. So it's going to have a solution in the form of e to the RT. You can figure out the indicial equation real quick. And it's got a solution of R equal 1, but with multiplicity 2. So that says our 2 solutions, y sub h, our 2 solutions are going to be e to the t and t e to the t. I'm going to refer to the first one as y1, the second one as y2. Which one you refer to as which doesn't matter as long as you're consistent, okay? So the system of equations that I'm going to have to sweat it over, I would put the e to the t and the t e to the t at the top row and then take derivatives until I make it square. E to the t, of course, is easy to take derivatives of. T e to the t requires you to use the product rule. Otherwise, it's not too bad. Then this column vector over here, if you had a higher order equation, it would have a bunch of zeros, and it would just have the right-hand side of the equation down there at the bottom, okay? Hey, by the way, notice that right-hand side of the equation was something that just would not have come out nicely. So that logarithm kind of makes things work awkwardly. All right, so we're going to get our W by just taking the determinant of that. So the main diagonal minus the transverse diagonal. And so you end up subtracting this t e to the 2t out, and you're left with only e to the 2t, okay? Then when we do our W1, we're replacing that first column there And so when you take the main diagonal, you're getting 0. And with the transverse diagonal, you're going to be saying minus t e to the 2t and log t. I didn't put those in any particular order there, but yeah. And then for the W2, you would take the main diagonal and get e to the 2t log t minus the transverse diagonal, which gives you just 0. So for your U1, you're going to have to divide the e to the 2t out, which you got from the Wronskian there. And so this turns into just t log t, all right? Which means that since that's U1 prime, we have to integrate it. So integrating it, just go ahead and do integration by parts on it. I indicated here the u and the dv and stuff. But once you do that, you should turn out to get 1/2 t squared log t minus 1/4 t squared, okay? And then we'll go to U2 prime, and that's going to have just that e to the 2t log t over e to the 2t, so you cancel, you end up with log t. We have to integrate that, and that is again an integration by parts dealy bopper. And I should put a C1 and a C2 there. So once you've got those, then you can say your y sub p is your y1, u1, y2, u2. For some bizarre reason, when I was writing these, I wrote a V down there, and it's supposed to be a U. All right. So you've got your e to the t times that mass, and your t e to the t times that mass. And then when you expand it out, notice that C1 and the C2 for your y sub h just hangs right here at the end where you want it to. Now, if you wanted to just get y sub p, don't bother writing down the C1 and C2, okay? But in any case, when you get to simplifying, you come out to this horrifying mess, right? But then plus the y sub h there to give you the general solution. All right. I'll upload the notes for that later. So let's go ahead and take a look at a second example here. And this is going to be one of our equidimensional equations. All right. So with our equidimensional equations, they are linear. And so we can do that same thing about the homogeneous equations. It's just that in this homogeneous equation, we've got something that's equidimensional, so we have to pull a different trick for it. Instead of assuming that our equations have the form e to the rt, we instead assume that the form is going to be t to the r power, and that means we've got r times r minus 1, and minus r, and then plus 1. So just like before, we actually even get the same polynomial for it. So we've got r equals 1 with multiplicity 2. But this time, our y sub h will be c1t and c2t log t, because equidimensional equations are different than the constant coefficient ones. So, and for our y sub p, we take and put a u1 with the t and a u2 with the t log t. And then we go ahead and put things into the matrix here. So t and t log 2 across, this is t and t log t across the top, and their derivatives across the bottom row. So when you do the Wronskian, you'd multiply the t here and get t times log t plus 1 minus the t on the transverse diagonal. So, I'm sorry, the transverse diagonal, the t log t. And so the Wronskian you get is just t. Seems too nice, didn't it? So, all right, so for your W1, you're replacing that first column with 0 and t, and that means that you end up with just the negative t squared log t. So your U1 is that divided by T. So you've got T log T that you have to integrate here. So that, of course, is super thrilling. I think we did that one last time. But in any case, though, we end up with the minus 1/2 T squared log T plus 1/4 T squared plus C1. And then for doing the W2, we end up with T squared minus 0. So the W2 is T squared, and we divide it by the T. And so we end up with just T for our W2. So when you integrate that, 1/2 T squared plus C2 if you wanted. So the Y sub P, you're going to take your T and multiply it by that mass. And you're going to take your T log T and multiply it by a smaller mass. And lo and behold, magic happens. It's sometimes it's frustrating how often things cancel out in a nice way, but we're left with just the 1/4 T cubed. Okay. So that means your general solution, y of t equals 1/4 T cubed plus C1T and C2T log T. So up at the top, I had initial conditions, which you'll have to just remember where y of 1 equals 1. And when you just plug in and find out, well, C1 had to have been 3/4. But then the y prime of t, I've got to go back and take the derivative. Assuming I did that right, when I plug in, I should get 3/4 plus C1 and then plus C2. And that is being set to equal 4, which lets you solve it down and get 5/2. So your final solution here has the 1/4 T cubed, the 3/4 T, and the 5/2 T log T. With the proviso, of course, T has to be greater than 0 because, you know, logarithms and stuff, you can't plug that in. All right, so I know that I ran through that quick. One of the advantages of having these videos is that you can actually go back and hit pause in order to see what the details were of those. So these take some work, and it's just a lot of bookkeeping. But when you've got something on the right-hand side of your differential equation that you can't guess your y sub p's for, this is what you got to do. Okay. All right. I'll see you in class.